Oh, I got you. At least you got back. People are stranded on the East Coast still. Yeah. No. I've got students at 243 that can't make it yesterday or tomorrow because they're starting to work. Everybody's getting winter except us. Although hopefully right now it's like.
I hope so.
Have they got any up there?
I don't think so. I checked last night.
Okay. The cross plate slipped out at Junior this morning. Yes. But then I realized it's 34 degrees and went, I'm going to be 28.
We were planning to do 4 days in the back.
Oh, yeah. You probably still can't just bring your mountain bikes.
Bring my mountain biking instead.
Bring your mountain bikes and a large pair of boots in case you don't home. Well, welcome back. Thanks for coming back. Anybody lose earrings? They're quite nice.
You can have.
I will wear them. So anyway, thanks for the quiz. Hopefully it wasn't too challenging. It changed a little bit. I know it looked the same as the one you guys took last term in 243. I had to change the wording on a couple things to make it match the new quiz thing and the new exam thing. Because like one of the things was if you missed the day an exam is given in class, well we're not going to do that anymore. Taken out of class. So anyway, I think it's the same pattern as answers though. So the point was just to get you to that page and making sure you looked at it. So if you looked at it last term, you're probably still voting, and you know how things work around here. I'm going to post at least one, probably two, maybe even 3 quizzes for next week. The way I'm looking at it is, that sounds awful, I know, but remember you don't have to do all of them. You pick whatever ones you want to do. I think the way I'm going to do it, I'm going to have a confidence interval quiz, which probably makes no sense right now. That's what we're going to start talking about today, and we'll keep talking about it on Monday. Probably a normal distribution review quiz from 243, bell curve stuff, being able to pull areas off the bell curve. I'll throw one of those up there. And maybe a central limit theorem review quiz too. That was the very last topic we did in 243 with the funny dice, where you had to generate samples and find bell curves. Since that was at the very end of 243, we didn't have a whole lot of time to let it kind of sink in. So maybe I'll throw one of those quizzes up too. So, you know, do 1, 2, 3, none, whatever you guys want to do. We have an in-class quiz to do today, so I think between that, the in-class quiz today, and the 3 posted next week, that's half of your quiz allotment for the entire term in 2 weeks, should you choose to do them all. So, don't worry. I guess what I'm trying to say is don't worry about the 10 quizzes you have to turn in. There's going to be plenty of them around, and I've probably got at least 1, if not 2 more for next week to do in class together. So, we'll have plenty. Thank you. So, let's see. Where are we right now? Besides MODOK. We had just finished, we had done the card experiment in class last time. Yeah. Card experiment in class, yeah. Says, yes, we did. Good. So why did you say it that way? Yeah. Because you stacked the deck. Because I stacked the deck. Claim. Yeah. Agreed claim. You can't prove that. You did a different deck with me today.
You said you did that.
Right, I shuffled them. You saw me shuffle them. I suck at it. You saw me shuffle them. Right. You saw me shuffle the cards each time. I wouldn't let you can't see them, Michael. You know that.
But you shuffled it so we couldn't see them.
You were very sneakily.
And you told us.
It doesn't matter if I shuffled them the right way. You couldn't see it anyway. I would have tilted it back. You wouldn't have. You can't see your population. That's the whole point, right? Yeah. You're right. I was sneaky about it, but the point is, I had to be because you're not allowed to see your population.
Says who?
Says everything. I want to know the average age of a Democratic voter in the Pacific Northwest. Go count them all, my friend. You can't. Kate knows that. Be with it. Godspeed, my friend. What's he saying? But as we said, tell me your name again.
Deanne.
Deanne mentioned yesterday that that population that I had was so small we could have counted it. It's a deck of cards, 52 things in it. And in that case, we throw statistics out altogether. What is statistics? What does that word actually mean?
The given point of data.
Where? Good. It's a given point of... Actually, can I change the word? It's a given measurement of what? Of a what? Not a population. Of a sample. A statistic is a measure of a sample. I know this is one of those things that, because it gets misused all the time. Very often you talk about baseball player statistics. False. Those are statistics for a baseball player. That's the word that's used. And go ahead and keep using it because we're not going to change America's way of discussing national pastime. But that's everything that happened with those. When they say that the player has 32 RBIs or 16, whatever, I don't know how to play baseball. So, but we know everything those players did. What are those called? Parameters. Exactly. Those are called parameters, Skylar. Those are called parameters. If you can take a census, you can actually get a parameter. So if I gave you the deck of cards, you could count it all out and find out how many red and how many black, and there wouldn't be any need for a sample. But the problem is, you can't do censuses. You can't do a census most of the time. Even the Census Bureau that does the census every 10 years is beginning to admit the fact that it's getting too damn hard, because there's too many of us. When the census was written into the Constitution back in whenever that was, 1775 and a half, there was like 12 people in America. Don't count them all. Okay, there's this horse. You know, I mean, it was easy to count them. Now there's 310 million people. It's getting harder to count them, so they're even beginning to admit that the U.S. Census Bureau is going to start doing random sampling, which they should have been doing for the past 30 years anyway, because it's next to impossible. They're getting a huge chunk, but it's the resources used to get that huge chunk aren't worth it when you can do just as well with a random sample. And that's what I want to get into today, is the whole idea of random sampling and how you estimate things from it. That's what today is all about. But I don't want to leave the deck of cards just yet, because I want to revisit it real quick, just to recap. I might even build another quiz around the deck of cards. We'll see how time goes. So these are the two claims that are available to us. The deck is fair, the deck is not fair. Those are the two claims. I know what you guys are claiming. You're claiming number 2 over there. Deck is not fair. And why are you claiming that?
Because life is not fair.
You hold that thought. Michael, go.
What happened only happened, I think we said 3% of the time.
Nice! Michael realized what we saw happen was an outlier. It was an outlier. It only happened like 3%. It should have happened 3% of the time. Now, if we keep doing the experiment over and over again with a fair deck of cards, you will eventually see 5 black cards come out first.
On the first time?
That's the kick. Yeah, on the first time. Eventually you will see it on the first time. But the kicker is, how likely was it that you guys saw it on your first time? And Michael just said, it's less than about 3% of the time, which is unusual. So there's a claim then made that the deck isn't fair. Love that. It's your first inferential claim. Awesome. Well, here's the deal. Since you don't know which one's going to be true, all you can do is make a claim based on your sample. Either say the deck isn't fair or say the deck is fair. Okay, that's what we do. Say the deck isn't fair, say the deck is fair. We start with that. Okay? Now, you don't know which one of these is right either. You know which one is most likely right based on your observations. That's why this course is called probability, because it's probable. It's probable. You go with the probable, not the unusual. Okay, now, the problem is, if the deck was fair, and it sounds like everybody's saying it's not, that means you made an oops. Because it actually is fine, and you just happen to catch the outlier event. And what do we call that? Well, we call it a false positive. Now, do you see why that's a positive test result? Let's make sure we can tie this back to 243 a little bit. I'm calling that a positive test result. Positive testing here implies that the deck is rigged. So if you come back with a positive test result, you're saying there's something wrong with the deck. Just like a disease test. When you test positive for a disease, it means the disease is in your system somehow. The disease in this case is being rigged. Does that kind of make sense? It's just how I'm choosing to define it. But I'm choosing to define a positive test result as something that deviates from normal. A normal deck of cards, we shouldn't have seen 5 black cards come out. So we're claiming the deck isn't fair. Therefore, we're positively shifting the belief that it's not fair. But we could be wrong. Maybe you just, remember, I taught this class for years and years and years and years. What if you guys were the first time I saw 5 black cards in a row?
You would have said something.
Would I have said something?
Yeah.
I'm fairly good at not saying things that I shouldn't. As hard as that is to believe, being the Italian diarrhea of the mouth that I have.
Last
But-
term it happened a couple times.
Don't
Yeah.
you?
Things were supposed to happen and they
Oh,
we did
were
the-
like-
Jack, you mentioned that one. That blew my mind. That blew my mind. Because of the likelihood of what happened in class with the 1, 2, 3, 4, 5, 6.
Yeah.
Thank God it didn't happen in order, because my head would have exploded had it happened in order. But whew, that was bizarre. It's not 3% is bizarre. It's an outlier, but it's nowhere near as unlikely as 1, 2, 3, 4, 5, 6. That's just stupid. I'm still shaking about that one. Now, however, if you say the deck is fair and the deck is fair, then yeah, that's correct. You did a good thing in that. Nobody's claiming that in this case. Now, this is a false positive. Do you know what this would be called? I'm just going to plant this seed now for later in the class. Do you know what this would be called? True, false, positive, negative. Pick one of each of those words, either true, false, or positive, negative. If the deck actually is fair, and you say it's fair, what would that be called? Would it be true or false, first of all?
True.
Good, it's going to be true. Perfect. It's going to be true because you were correct.
It'd be a true negative.
It would be a true negative. This is no, good. This is going to take some getting used to. A negative test result. Remember what we said positive means. Positive means the test is implying the deck is rigged. A negative test would therefore imply the deck is not rigged. And if the deck is not rigged, and we say it's not rigged, or we say it's fair, that's a true negative test result. That's like taking a disease test and it coming back negative, and you not actually having the disease. We discussed that briefly in that last project in 240. Yeah. We'll come back to that. If that's kind of like, oh, that was a lot of 815. We'll come back to that throughout the course of the course. But that's a true negative. That's a true negative. Yeah. What would this guy be? The deck is rigged. And you say the deck is rigged. What would that be? That would be a true positive. Because you were correct, that's what makes it true. And the deck actually is rigged and you caught it, which would make it a positive test result because you caught the positivity, you caught the shift from fair to unfair. Believable? Good. What's left? One case we haven't looked at yet. A false negative. A false negative. That would be this case because the deck is rigged, which means you should have said it was rigged, but you missed it. You called the deck fair. By saying it's fair, that's a negative test result. That's, yeah, we tested you for Lyme disease, and you don't have it. Meanwhile, my left side of my face gets paralyzed and huge rings pop out over my back. Please, Renee.
So the positive and the negative depend upon the question you're asking?
Basically, yes. And thank you for that question. Here's the way I want you to think about positive and negative test results for now. A positive test result means something has changed from what is to be expected. It's not necessarily a good or bad thing. It could be either good or bad. It could also be indifferent. It might be, for example, you're testing a new drug, and the drug is supposed to knock down headache symptoms in some other drug. Very often, pharmaceutical industries have their hands full building drugs to treat symptoms of drugs, to treat symptoms of drugs. It's staggering, actually. The more I read about ADHD, the more I realize I don't want to take the drug, because you have to stack them all together. So one time you take one drug, but that creates a side effect, and then the next drug knocks the side effect down. So if the drug is effective, it'll knock the side effect down. That's a positive test result, because you're expecting it to do nothing, and it actually knocks the side effect down. That's a positive test result. That's a good thing, yeah? That's a good thing. It could also be a bad thing. Suppose you're trying to see if cancer rates are higher in certain areas than in other areas. Okay, the assumption is they're exactly the same, or they're no different. But if you test, the movie, I think it's called Civil Action, with John Travolta was this dealt with a little town in New England. We went through this. The idea of that is, you've seen it, Harrison?
I heard about it.
Exactly, I think that's the idea of, I think that's the name of the movie too. But the idea is, there's a cancer rate in the town. If the cancer rate shifts either up or down, in that case it was up, that's a positive test result, because we noticed the cancer rate is higher. So that's a bad positive test. See what I'm getting at here? So positive just means shift from what's expected. That's the best way to put that in your mind right now. And we'll keep coming back to it. Go ahead.
So the negative means that it's...
Nothing has changed. So whatever you were expecting to happen, happened. Which means we didn't get an what? Starts with an O. Ends with an liar. Yes! If you didn't get an outlier, nothing unusual happened, which means everything's kind of right in line. And that's what I want to focus on today is, how do you know what in line is? What's in line? If we can establish what in line is, then we can establish what out of line looks like. Make sense? Good so far? Any questions about this? Ish. Okay, good. Shout them out if you got. I love the questions you guys have already. What I want to do real quick is I want to show you something that might make your head spin a little teeny tiny bit. But I think we'll get the point of this. Don't write this down, there's a lot going on here. Tons going on here. But I want to kind of come to a conclusion together before we move on. We have an experiment for us to do. But before we do the experiment, I want to make sure you guys understand why I'm not completely full of crap and why I'm putting you in these seats. Why do you need a part 2 stat course? Ray, would you mind just killing one of the lights? That'd be awesome, man. Thank you. What I've done is I've created, oh, that's perfect. Just comes. I've created a completely arbitrary population of 6 values. So even smaller than the card deck. Here they are right here. 0.61, 0.38, 0.71, 0.71, 0.57, and 0.9. What's special about them? Absolutely nothing. They're random numbers I generated using Excel. Pop up here, See that round, rand, comma 2? That means generate a random number and then round it off to 2 decimals. Each one of those is like that. So every time I press F9, just like you did back in 243, you'll get 6 more. 6 more of them randomly generated right there. No big deal. Pretty straightforward, yeah? That's your population. So that's what, technically speaking, you'd never ever see. That's hidden out there, yeah? Now it's 6. To which Dan would say, go count them. Yes, of course. But imagine that's like the entire country and the voters that are female between the ages of 18 and 24. And you're trying to figure out how to woo those voters over to your party. You can't go count them, there's too many of them. So the logic that we're going to attack with this population of size 6 is exactly the same logic with the population of size n, which we'll get into as we go through today. But this is a starter for us. What I've done under that is I've put a number of parameters down and their values depending on those 6. So remember mu? Remember that guy? Mu. Mu is another word for what? Perfect. That's your mean, that's your average. That's the average of the entire population. So that bad boy is the average of those values up there. Let me show you. Pulling your leg. Boom. Average of those 6 values. Yeah? Good? Median, right here. That's just the median value. In this case, it would be the median of 2 of them, right? It would be the median of the middle 2, because there's 6 of them and so forth. And then we've got sigma down here. We've got little sigma. Little sigma is the good. It's a standard deviation of whom? Of the entire population. And FYI, I don't know if anybody's ever going to need this. Oops. But we'll come back to that for a second. I put it as the square root of B20 because this standard deviation is the square root of what's called the... I didn't harp on this too much in 243. I'm not sure if Donna did. Sigma squared. Did she talk about that at all in 243? That's called the variance. I know I mentioned it once in 10 weeks, so I don't expect my 243s to know what I was talking about. It's the square of the standard deviation, which seems kind of weird. Like, why would you do that? And you don't remember doing it, but you calculated a variance one time for Bert. When we did Bert and Ernie, you had to start with the variance and then square root that to get the standard deviation. If you remember, we had to square the deviations, add them up, and then square root them. That's the one time you did it. And then we left it alone. Because the variance doesn't have any meaning for us in 243. It's got a little bit of meaning for us here in 244, but still not a huge amount. So anyway, the variance is in this cell down here, and that guy up there is the square root of it. And Excel, note, you see that little, you don't see it right now? There's a little P. It's VAR is the variance command, VAR. What do you think the P stands for after the VARP? P stands for population. Because it's the variance of the population. That way Excel knows you're taking the population variance and not the sample variance. I do not want you to lose sleep over why the hell they're different. It's a formula difference. And I don't want you to worry about it because it really isn't important. Just realize it is different, and if you ever have to calculate one versus the other, you have to let Excel know which one it is. Just put that in the back of your mind. You can always email me and ask me to. I'll be here for years. What else did I do? Oh, this is an interesting one down here. This actually relates quite a bit to today. This is the proportion of data greater than a half in the population. So I put bigger than, P bigger than 0.5. Let me slide that out of the way so you can see it. So what percentage of the data up there is larger than a half? That might not make any sense as to why you would care about that right now. Don't worry, we'll come back. So 0.59, that's bigger, yeah? 0.22? Nope. 0.78? 0.87? 0.76? 0.4? So 4 out of 6, 2/3, 0.67. Make sense? Let's do it again, make sure we understand what the hell's going on there. What's it saying it is now? It's saying it's 0.67 again. Yes, 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 no, yes, no. So 2/3 again, yes? Why would we care about this kind of thing? Now it's, what is it? It's 0.83 now. 0.83, let's see, that one is, yeah? Yeah? No, no. Yeah. So there's 5 out of 6, which is 83%. So the choices for that one are going to be 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, or 100%. All 6 of them might be bigger than a half. Why do we care about a ratio bigger than a half, do you think? Any idea? You might not have an idea right now, and that's okay.
It's 90.
Please, Kate.
Well, if it's out of 1 being the max, that's your 50th percentile.
Good, that's your 50th percentile. We care about it. How many times have you heard the majority believe? Or the majority don't believe, the majority. In the news it happens all the time, right? The majority means more than 50%. So we like to be able to quantify these quartiles, 50%, 25, 75. whatever percent we need. I picked 50% somewhat arbitrarily. We could measure any percentage we wanted to. It just seemed like 50 was a nice normal place to start. But yeah, we do like looking at those probabilities based off of data, which is what today is really all about. And probably, what's today? Wednesday? Yeah, and also Monday. Cool? Good so far? All right, what else are we doing? The average deviation. You guys actually invented this last term. I don't remember, you don't remember doing it. The day we did Bert and Ernie, before we did Bert and Ernie, I told you guys, come up with a way of measuring Bert and Ernie's variation. Because everybody was saying, Bert's more consistent, Ernie's more random, more variable. I said, good, quantify it. He said, what do you mean? He said, well, give me a number. And then I let you loose for like 10, 15 minutes, and you all kind of work with each other, which was great. And then somebody, I forget who it was in which class, came up with this measure right here. It's called the average deviation. Nobody uses it, you're about to see why. It is really intuitive, and I love it. I love it. Remember what the average deviation is? You could say no, because it's been literally probably 10, 15 weeks, but Christina, go.
The distance on average that is from average.
And it's literally, yes, the mathematical distance. Now, I taught you guys to say, on average, the distance from average for the standard deviation, for this guy. And I want you to keep thinking of it that way. But this guy is the actual mathematical average distance. And when I say that, that means take each data point, figure out how far it is away from the average, take the absolute value of that number. If it's positive, keep it positive. If it's negative, make it negative. And then add all those up and average them. And that's what the average deviation actually is. Notice it's close. Where's sigma? 0.27 to 0.17. It's close-ish. Not the same. And there's a very good reason why nobody uses it. You're about to learn in about 5 minutes why nobody uses it in statistics. Okay, there's a good reason. It's a great it's very mathematically precise. It's intuitive. Every time I ask a class to think up one, they always come up with that one first. It's brilliant. Nobody uses it. And you're going to see one pretty good reason as to why. The mode, if we have one, hell yeah, we got lucky this time. We actually have one. It's tricky to get a mode with only 6. Very often you'll see a does not apply down there. Not applicable, not applicable. There's a 0.49. So very often you get a not applicable because with 6, it's just too likely not to have a match. Remember what the mode is, right? Yes. The mostest. Yes, good, the mostest. Love that. Range, remember what that guy is?
If you take your highest number and your lowest number and
Exactly. The distance between them. You got it, Kate. The distance between the highest and the lowest, and the distance between 0.26, I guess, and 0.99. There's your range down there. And last but not least, the skew. This is one of my favorites. So we're going to come back to this in this class a little bit here and there. We talked about it briefly in 243. What does skew sound like? What is that? What does it sound like we're talking about? Tell me your name back there.
Debbie.
Debbie, go.
The way it kind of goes to one side or to the other side.
Exactly right. It's how it leans. We like to compare things to bell curves in here, yeah? We like bell curves. Bell curves are symmetric. They're unimodal. You can still have unimodality, but then sometimes the curves can lean to one side or the other, and skew's a measure of how much they lean. I think mathematically how Excel is calculating is it's looking at the median and the mean, and it's measuring basically weighted with the standard deviation how far the mean is from the median. When the mean is to the right of the median, you get a positive skew, and when it's to the left, you get a negative skew. When it's 0, you don't have any skew. But remember this formula? Hopefully you don't, actually.
If it's larger than 2 is great skewedness.
That was great skewedness. Yes, that Pearson skew coefficient did. The guy's name, I forget his name now. He made up a scale, basically, that said if it gets bigger than this, it shows somewhat skew. Bigger than this, it shows great skewness. Exactly. I don't want you to get hung up on that kind of stuff because nobody really agrees with what great skewness is. We're going to get back in the habit of looking at everything, looking at, not right now, but looking at visuals of data and trying to see if we even should use things like averages or if averages might be misleading. So, good. So there are 9 parameters based off that population right there. And there are 9 diagrams here based off those. Each one of those bad boys gets a window. So what I want you to do is kind of familiarize yourself. Here's your average right here. The parameter in each is a little green triangle. So you can find it. There he is right there. Notice the scale is between 0 and 1.5. The parameter value mu is 0.44. That's why it's right about there. Just south of 0.5. Okay? As it moves around, it's going to change. Let's move it for you so you can see. See how it's bouncing around with the value of mu? It's moving around left and right. There your skew is negative. Very negative. Is everybody following that? They're following that parameter? Good, good, good. I'm going to plot the parameter in the same place on each graph. Here is the median. Right now the median looks at 0.73. That's where 0.73 is. Sigma's at 0.19. Where's sigma? It's not there. Where did I put it? Oh, here. Here it is, 0.19. Oh, I didn't put them in order. That was kind of annoying. Mode. There is no mode right now. So there's no mode on the chart up there. So don't worry about that. We'll come back to that. Skew. Negative 0.58. You guys have seen the point. Yeah, you see what's going on? Good, 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 good. Now, let me explain the other things on those charts besides the parameters. I think we get the parameters. We understand what's going on. You see all these blue dots up here?
Better population.
Ish.
Numbers.
Yes.
But it's not the 6, it's
What I've done is, using Excel, and I don't know how to turn these off. That's all these green triangles back here. They're hidden because it gets very distracting with those turned on. I've taken random samples of size 2 from that population with replacement. So in other words, I've drawn 36 samples, every possible sample drawn from that population. So the first sample, 0.76, 0.76, 0.76, 0.7, 0.76, 0.4, 0.76, 0.42, 0.76, 0.86. Done that 36 times, just like rolling a die. Think about it that way. It's like rolling a die and keeping track of all the outcomes. Exactly, every single one of those outcomes, 6 times 6. And I did it with replacement to keep the math easy. Those blue dots up there, those represent the averages of each of the 36 samples. So each of the 36 samples has an average. It's pretty annoying because there's only 2, so you do this plus this divided by 2. But each one of those averages is placed right there. Does that make sense? I do the same thing with the medians. Each one of those medians is placed right here. There are far, far fewer medians than averages because you're going to have a lot more overlap with the medians. A lot more overlap. There's the modes, all the samples with modes. You're only going to have 6 of them, right? You're only going to have a mode, I guess, when you draw one sample with itself. So there's only going to be 6 that have a mode. Here's all the skews, all the possible skews of those samples, all the possible standard deviations, all the possible variances, and so forth and so on and so forth. Very few proportions, okay? And there's all the average deviations. Notice every time I press F9, those guys bounce around too. They bounce around as well, yeah? Thank God. Imagine doing this by hand. Crap. Setting it up took hours, but then it's done. Sweet. Just change the numbers if I have to. Okay, everybody happy with what the blue things are?
How did you get the median samples?
Same exact thing, just drawing the values and then plotting the medians up there. Which the problem is you get quite a bit of repetition.
But there's only 6, so but you were drawing 2 at a time?
Two at a time.
36 times.
Oh, I see your point. Oh, I see. It should match the averages. I've got it drawn the wrong way. I've got it selected the wrong way in the Excel sheet. I'm going to fix that at the break. Thanks for pointing that out. I didn't even think about that. They should match the averages perfectly because you're pulling a value and pulling a second value and dividing by 2. I'm going to fix that at 10. It's not going to matter. Thank you for that. It's not going to matter at the end right now for the argument we're about to make, but it will be good to have it fixed for the future. Thank you very much. I didn't even notice that. Now look at the red square that's up there. Can you read the text on what that is? Right, so it's the average of all of those things. So in other words, take all of these values here, average all of them, and put that right here. And then it moves as well as everything else moves, it moves. Bounces around with it, yes, bounces around with it, good, good, good. Now that we know what the hell everything is up there, now I want to ask you, why did I color 3 of them yellow and leave 6 of them white? And I'll bounce it so you can watch. Don't call this out if you see what's going on. Look up at me once you see why I colored 3 of them yellow. What's special about those 3 and what the other 6 don't have? You got me thinking about why I grabbed the wrong.
That looks more like the mode of the green.
It is. It's matching the mode.
Yeah.
I've got the wrong cells collected. It should look just like the average. You're right, because an average of size 2 is the exact same as a median of size 2. I've got the wrong data selected. Thank you for catching that.
I don't know the other. That's good.
But it wouldn't work for the median anyway. Is anybody seeing what's different about it? Let me see hands if you are seeing it. Okay, let's keep look. Here's what I want you. Let me give you one more hint. Look at the parameter value on each one. and look at that average of samples on each one. What's true every single time in the yellow ones? What's true? Dawn, go!
They match.
Every single time with the average and the proportion and the variance, the parameter will line up with the average of the samples.
Look at the one you have right now.
Oh, that's another Excel error, which I have to fix, because, no, it has to mathematically.
Like, except for the
There's an Excel glitch going on. It has to
It
mathematically.
did on all of them up until now.
Yeah, it did. Well, it has to, mathematically it has to. This is just Excel showing me that it has to. Whew. I should have left it and taken a screenshot. Damn it. I won't do it again. Watch. But mathematically it has to. Now, I'm not saying it can't happen elsewhere. It can happen occasionally elsewhere. But it will always happen, except for that one freakish time right there. It will always happen with those three parameters and those three average statistics. Now, you guys already knew this for one of them at the end of last term with the central limit theorem. You already knew that happened with this guy. That's what we discovered with those dice last term. On average, the averages, exactly, on average, the averages target mu. But they also target the population proportion that's out there. And they also target the population variance that's out there. Now, this one we don't care about too much. We'll come back to why. But, JC, go, please.
So if you change the proportion for P to be greater than 0.2.
Awesome.
whatever it
It'll
is,
still match. And unfortunately, I can't do it right here because I have to get in the guts and change it too. But it wouldn't matter what proportion you used. It would still target it. Thank you. Great question. Fantastic question. Yeah. Did you hear JC's question? The 0.5 proportion that I'm testing against right now is somewhat arbitrary. I just used a half because it's one we hear a lot in the world. JC's was like, JC asked, what if it was 0.2 or 0.72 or 0.8 or anything? Doesn't matter. As long as it's proportion in the population, the samples will target it as well. Kate, go.
So if your median's supposed to look just like your average, should that one be
But the sample of those medians won't target it. That's what I need to get back in and look at what the hell happened. I know, it should look just like it, but the samples themselves aren't going to weight the same. So the values might be the same, but the weights will be different because of the differences in the calculations. I saw another hint, I thought. Let me sum this up. Let me shut this guy down. Ooh, hang on. Shut her down. Don't save. I'm going to fix you. Don't need you yet. What, and I'm going to have this posted for you. I'll have this posted for you, so you don't have to write this stuff down. The three things we just mentioned, mu, population variance, and population proportion. We're going to start calling that guy little p. Just he ties in with the binomial that way. Those guys, on average, are going to be targeted by x bar, s squared, which is a sample variance, and p hat, which is a sample proportion. He's the guy we're going to get talking about today. P hat. P hat. Apologies to all the nurses out there who call P hat something else. Okay? But, to make it easier for us, let's not talk about this one throughout the course of this term. Let's just talk about the average and the proportion. Now here's why. Well, there's a couple reasons why. Here's one reason why. Because there's not enough time. There's just not enough time to talk about all three of those and get a deep understanding of all three of them. That's one reason. Second reason is, nobody seems to want to talk about this one in academia, and in one of the rare cases where I actually agree with academia, I do agree. It's not worth talking about, in my opinion. Talking about variances, you don't measure variance in your lives. You measure deviation. You measure average or standard deviation. You don't square that result when you're done, because as soon as you square that result, you get a unit that doesn't match your original unit, and you have to deal with transformations, and it's annoying. If those of you taking more statistics classes may have to deal with this, and you'll deal with it then. Even if we're going to learn it now, you forget it by then anyway. And most of you won't ever have to learn it. So I'd rather focus on the two things that you actually see in your lives all the time. Average amount of time till a child walks the first time. The percentage of appetite loss on a certain drug. Average weight gain for bulimic patients, or weight loss for bulimic patients, or weight gain for anorexic patients. Proportion of underage drinking in certain regions after certain dates. That's the kind of stuff you hear about in the news, and that's the kind of stuff I want to study. I don't want to study about variances of Tour de France cyclists or things like that, because it doesn't make any sense to analyze that kind of stuff. Does that make sense? So of those three yellow things, let's just can the 1 and focus on the last 2, and we'll start with 1 today. But that means we have to deal with one thing, and that's called sampling error. Now, sampling error, you may have noticed, maybe you didn't. I had you focus so heavily on the square and the triangle, you may have stopped looking at the blue dots, yes? That's the average of all the samples. Yay. And it's exactly equal to that triangle. Yay, squared. That was the exact terms from last term. Gesundheit. The problem is, you don't get this in a study. What do you get? Which piece of this are you going to get in your study? You get one of those up there. You do. You get one of the samples. Tell me your name again. Madeline, thank you. Madeline's correct. You're going to get one of those samples up there. One of those blue diamonds you get. Okay? If you replicate a study, you might get 2 of them or 3 of them. But you don't get more than one of those blue diamonds. So if you get this one, you're like, hell yeah, I'm pretty close. Hell yeah, I'm not quite as close. Oh God, I'm not close at all. Right? You can get pretty far away. That's called sampling error. And you have to accept that. Think back to 243. Rolling the funny dice in 243. On average, those bell curves were sitting right on top of mu, yeah? But it was a bell curve. There were some that were pretty far away from you. They got more rare as they got further away. Yes, they got more rare. But some of them got pretty far away. So what we need to do, we're going to start it today, is figure out a way to mitigate sampling error. Does anybody have any idea how you do that?
Take more samples.
Say that again. Be nice and loud.
Take more samples.
Say that again, I still can't hear it. Sorry, I'm deaf, I'm a punk rock drummer. Oh, Renee, go!
Take more samples.
That's one way to do it, yes, but there's still going to be error with more samples. But what's going to happen to the error? What's going to happen when you take more samples? Nice, good. Anytime you draw a sample from your population, you're going to have error. So the way you mitigate it, as Renee correctly pointed out, is you attach wings or an interval around your estimate. So this is Madeline's center that she gets. It's pretty far out there, yeah? It's pretty far out there. But that sample also gets wings, which we're going to start learning how to calculate today. The margin of error. Yes, we mentioned it quite a bit in 243, but we never talked about calculating it in 243. I said, just wait, we'll get to it, and now we're here. So the idea is you slap a margin of error on your statistic, and then, instead of saying, this is what I think mu is, you don't say that. Exactly. You say, I think mu might be as small as this, or as large as this, or anything in between. And the idea is you try to catch mu in the net. You try to catch mu in the net. You throw in the net can be very wide. Now Renee mentioned the way to make the net smaller, yes? You can make the net smaller by increasing your sample. We'll get more on that today. We'll see why that happens. And some of you might say, wait a minute, I don't want the net to be smaller, because if I make the net much smaller than it is right now, I'm going to miss that value of that green diamond, yeah? And that's true. But the point in fact is, if you make the net smaller, that blue diamond won't be as far right as it is right now, which might not make any sense to you as you're sitting there like, okay, now it just seems like magic. It's not magic, I promise. There's good mathematics behind all of it. But we're just kind of giving you an overview right now of where we're headed. But now you really got that glazed look. So let's kick you out of here for 5. We'll get some air, get some water. We'll come back. I'm going to fix that damn Excel sheet. I'm going to tell him. The only thing I can think of, maybe it's samples of size 3. No, it could be right, actually. If I drew samples of size 3 and not 2. Let me take a look.
Hey, real quick before you go run away.
I'm not going to run, I'm going to stay.
Oh, never mind.
I have to fix that Excel sheet. Sorry, YouTube, you didn't need to hear that.